covering today are two topics. One's on analytics. We'll be going a little deeper into statistics, but not in a very way. In fact, I don't even have a don't panic slide today. It's going to be quite easy. And second half after tea, we'll be talking about different kinds of visualizations and what are the ways in which one can take data and represent it in a pictorial form. Unfortunately, I will be receiving a call in a few minutes, which I have to take. My apologies. We'll take a short break during which Rajesh will be covering something else. So, pardon me for having this right into the class. It was quite unavoidable. Now, let's start with covering our three topics: variation, centrality, and significance. Don't worry about any of those terms. We'll talk about them as we go along. Let's say we had this kind of data. We have a bunch of mutual funds, and these mutual funds are, well, they have an NAV as of a given point in time. Since they're equity mutual funds, you would want to see what their performance was with respect to Sensex. So is it beating the Sensex on any given day? Is it performing versus the Sensex on any given day? And this incremental difference is in the financial circles called alpha. So alpha's your daily return compared to the Sensex. So supposing the Sensex grew by about 13% yesterday, and your mutual fund grew by 16%, the alpha is plus 3. If your mutual fund grew only by 10%, then your alpha is minus 3. And here's a simple plot of the actual alphas as of about a week ago. You can see a bunch of red dots. Each dot is a day, and these are the days on which ICICI Pru Focus Blue Chip was performing worse than the Sensex, and it was performing better than the Sensex on certain days. Now, if it's far away to the right, then it was significantly outperforming the Sensex, and if it's far to the left, then it's significantly underperforming the Sensex. And these are the
zero.
Zero is not actually drawn, but it's the dividing line between the reds and the blacks. So, and zero is actually the Sensex. And what you see, for instance, here is ING large cap equity is rather clustered around zero, so it's not straying too far away from the Sensex. Whereas ICICI Pru Indo-Asia equity is straying quite a bit from the Sensex. So is the HSBC mid cap equity. DSP BlackRock is by and large focused, is staying close to the Sensex. To a certain extent, so is Tata Equity, TND. And that gives you a sense. So you can ask the question, look, what's the variation in their performance? And the intuitive answer would be, looks like there's a fair bit of variation in HSBC's performance, in ICICI Pru Indo-Asia equity performance, but not as much in the ING large cap, or even to a certain extent in ICICI Pru Focus, the variation is a little less. Now, what are the ways in which one could measure this quantitatively? Any guesses? If I ask the question, what is the variation in alpha? What is the variation in the returns of a mutual fund? How would you measure it? If I asked, what is the variation in the height of the people in this class, how would you measure that?
First we need to find a mean.
Okay, so first find the mean, okay.
How far are they from?
How far are they from the mean? Okay, that's a possible measure.
You need a starting date and an end date.
Starting date and ending date, okay.
Over which you would do.
Fine, fine. So let's say it's over a 1 year period. We have the data for that.
An average from the deviation from that mean over that period.
Average of the deviation from the mean over that period. That's a possible measure.
We want to make sure that variations, whether positive or negative,
Are factored out. That's something we want to factor in. What is the simplest measure you can think of?
standard deviation.
Love that response. I love that response. Standard deviation. Simplest measure. 10 years ago, there was a girl in statistics class that I was taking who asked me to explain standard deviation. Sort of managed to get around it by giving something that sounded convincing, but wasn't quite, at least didn't convince me eventually, but probably convinced most of the class, or at least they said, okay, yeah, here's something that I broadly get, but I don't quite understand. Standard deviation is quite a complicated and unusual concept for whom we have one mathematician to blame, Carl Gauss, who, in the early 1800s created this simply because he found it easier to differentiate, as in calculus differentiation, than, for instance, the metric that you're proposing, which is the average and the absolute deviation. He said, nah, that's too complicated for calculus. Let's just pick something that's easy for calculus. And since then, we've been living with his since. Not since, he's taken statistics, and he and a number of others have taken statistics a long way from an analytical perspective. A brief interlude. Have you heard of this what used to be a famous problem called the solution to the quintic? Okay. Do you know how to solve? How many of you know how to solve a quadratic equation? That's practically everybody. Now the good part about the solution to a quadratic equation is that if you have ax squared plus bx plus c equals 0, then using a, b and c, you can figure out that value of x for which the value of that value of x for which this equation has a value of 0, which is nice. Now you could actually do that for a cubic. You could do that for a quadratic, meaning if you have x bar 4 plus x bar 3 plus x bar 2 plus x bar 1 plus x bar 0, which is 1, and put in coefficients for all of those, you can still solve it. But it turns out that for a quintic, it's just not possible analytically, meaning there isn't an equation to solve it. And this worried people for a long, long time. Today, almost every single problem that you see on a daily basis probably is a larger polynomial than a quintic, and you don't even bother trying to solve it. If you had that sort of a system thing on Excel, you just do a goal seek. There's this option called goal seek and say, tell me what combination of values gives me something close to 0. You don't bother solving it analytically, you just let the computer solve it. Now, for a long time, this wasn't the case. People had to solve it, and not only had to solve it, they had to find out the properties of it in an interesting fashion and do more analysis on it, and they didn't have computers. So a lot of statistics was developed to make sure that it was easy to manipulate it on paper and pen. Very little statistics was developed, at least till the 80s, to make it easier to manipulate it on the computer. Standard deviation was one of those classic things which was developed for paper and pen. Let me get up to standard deviation from something that is far simpler. We could, for instance, simply take the range. Say, tell me the highest value and tell me the lowest value, and the difference between those is my range. As simple as that. Any thoughts of what could go wrong with this or what trouble you might have? About the fact it's
extreme values.
Exactly. So now you've got this little data point that's going to kill the average. If this were far out here, then it would look like the range of the second data set was substantially more than the range of the first data set, while most of the data points are really clustered around this range. So how do we avoid that?
But what you want, isn't the question going to determine what you want? Sometimes you want to avoid those extreme things.
Sometimes you do, and sometimes you don't, and you just jump 4 slides. No, absolutely. The key question is, why are we trying to do this? But let's hold off for a moment and say that we are trying to measure the range for whatever reason, and we have a problem that there are some extreme points that causes some trouble. How might we get around that?
It depends. It's okay to ignore them, we can ignore some extent, like plus 5% or 1%.
Which is what most people do. So let's just knock off the top 5% and the bottom 5%. Now, the trouble with that is, why 5%, or why not 2%, or why not 10%, or is there anything in the data that we can use to figure out this in a dynamic fashion? It's not. Let's take another possibility. Instead of 5%, we say 25%. Knock off the top 25% and the bottom 25%. That's called the interquartile range. And what it does is tells you the spread of exactly half the values. This is also a popular metric. It's a lot more robust than the range. Now, this word robust has a very specific meaning. What it means is that when you toss some extreme values at it, it doesn't affect the number that you get. Supposing you added a really large number to this one, and a really large number to this one, the interquartile range is not affected. Nor, to be fair, is the 5% to the 95% range. So these are relatively more robust statistics as opposed to the range, which is not a robust statistic. One could go to any direction. Say, I could take every pair of points and find out the distance between these and take the average of those. That's a perfectly valid measure. Saying, on average, if I take any two numbers, the difference between those is something. And that roughly represents, that's a very good measure of the spread in the sense that I'm considering every single pair of points and not leaving anything aside. If there are some points that are really far away, then I'm factoring them in, but that's just one among n square points, where n is the total number of points, roughly. The trouble is this could take a long time to calculate, even for a computer. This is something that would take quite a bit of time to calculate, and this is a metric that I've very, very rarely seen used in textbooks because it's way too long to calculate, and in computational books because there are better measures than this. Which brings us actually to the question that you're talking about, which is why are we doing all of this? What is the purpose of measuring variation or the purpose of measuring any kind of range? Most often we do this to calculate some kind of loss or risk or error. Meaning, look, I'm going to make a decision based on this data. If I get it wrong, then how far off would I be? How bad would things go? For instance, if I were trying to make an investment decision based on the mutual fund returns that I saw, then what I might be interested in is how do I minimize my loss? So, which is a very different thing from saying how do I maximize my profits. When you're saying how do I minimize my loss, you're saying I don't care if I only go slightly above alpha or even slightly below alpha. What I'm making sure is that my worst case is not a terrible number. Or you could say I am interested in maximizing my profit. This is like my hedge fund. I want to make sure, I'm just trying to maximize my profit, which is what I'm likely to get most of the time is a good number. Or you could be saying, look, I'm not going to invest the bulk of my money into this. I've got all of that sitting safe in government securities or fixed deposit or whatever you wish. But I've got a relatively smaller portion of my money on which I want to take a huge risk. So I'm not worried about how many losses there are. I don't care about how bad those losses are. All I care about is that there is a small chance that the returns could be extremely high. This is in fact the venture capital's model. Because of the nature of the startup industry, the hits are so huge that, for example, this company called Y Combinator, they've invested in several hundreds of companies. And there are only 2 companies which have given them the bulk of their profit. Not that the others have not given them any profit, they have small profits. But the nature of the profits in this industry is that the big ones are so massive that they outweigh everything else. Let's take a simple example. If I were forming a new country, okay, and I want to make sure that this country has a really good GDP. Now, I could invite a lot of reasonably wealthy people. So let's say I have this room. I could pick the top 3 wealthiest people in this room and say, look, I'd like to invite you to my country because we'd have a high GDP. But all of that would not matter if I somehow managed to rope in Bill Gates. The VC returns are sort of like that because Y Combinator had invested among others in Dropbox and one other company. The profits of these companies were so massive that nothing else matters. So that's another kind of investment. In that case, what I'm trying to maximize is the value of the largest possible, no matter how unlikely it is. So these are all different kinds of error functions. Let's take some problems. So let's say I am dieting and I want to measure the calories. Now there are, like we saw a couple of lectures ago, there are a number of different foods and each of them have a certain calorific rate. And I need a reasonable number of calories to survive per day, and beyond that it's a bit of a problem. So let's say that I want, I don't know, how much does a human need per day?
2,500? 2,000?
3,000.
2,500.
2,000.
Depends on his size.
Okay, so let's say for a given person, the doctor said it's got to be 2,000. Let's just pick a number. And below 2,000, you're not getting enough. Above 2,000, you're getting a bit too much. So on average, try and make sure that you're staying in this much. Now, so supposing I took a bunch of foods, or I measured my calorie intake every day, then what would my error function possibly look like? What would my variation be? So if I took 100 calories less on a given day, or 100 calories more on a given day, that would probably be twice as worse as if I took 50 calories less or 50 calories more. And if I just took 1 calorie less or 1 calorie more, then, and the reason for that is I can make up a deficit of 100 calories by eating, let's say 10 extra calories 10 times. It's more or less additive. So one could take the absolute deviation in this case and take an average of those and say that that's my error. I sort of want to, sorry, not even absolute deviation. You actually just want to take a deviation and make sure that it averages up. In this particular case, the error function is simply the difference between the actual calories you consume and the ideal number of calories you've got to have. So that's a very simple error function. And the way to optimize it is to make sure that at after n days, you have eaten 2000 times n calories. If you've got a shortfall, you can cover it up. If you've got an excess, you can cover it up. Of course, all of this assumes that calories are linearly additive and you've got perfect willpower and all of that, but we'll grant all these assumptions. What if you're a fund manager and you're tracking an index? So what this means is there are these things called index funds, and the purpose of an index fund is to make sure that you track the index almost exactly. So which means that if you've got Sensex going up by 13% today, your fund should also go up exactly by 13% today. Now, this is possible to do it perfectly if the composition of your fund was exactly matching that of the Sensex. Now that is somewhat difficult. Supposing for instance the Sensex was a combination of just two stocks. The first stock had a million issue, and the second stock had so there were 10 stocks of the first company out there in the public and 5 stocks of the second company out there in the public. So now I've got to have an exact mix of 10:5 in my portfolio as well. So I've got 3 stocks of the first company. I need 1.5 stocks of the second company. Now there's no such thing as 1.5 stocks. So I've got to have either 2 stocks or 1 stock. So the way I try and track it as close as possible is today I'll have 1 stock of the company, tomorrow I'll have 2 stocks of the company, day after I'll have 1 stock, the day after I'll have 2 stocks. So I'll try and average it so that my portfolio matches that of the Sensex as closely as possible. But on every single day I'm making a slight error. Now my bonus is going to be based on how well I track this index. So which means that if I'm above by 0.5%, my bonus goes down by 0.5%. If I'm below by 0.5%, my bonus goes down by 0.5%. So in this case, my error function is the absolute value of the difference. Doesn't matter whether you're positive or negative, and I can't make up. I'm losing my bonus every single day. So that's another way of having an error function. What if you were writing an objective type exam? Your answers could be A, B, C, or D. It doesn't matter whether you get, if the answer was B, it doesn't matter how close you are or how far you are. You get it right or you get it wrong. In this case, the error function is a 0 or 1. Get it right or get it wrong. Simple. Similarly, if you are conducting a class election, either you win it or you don't win. Either you vote for the winning person or you don't vote for the winning person. It doesn't matter how many people are standing. That's another case of a 0-1 error function. What if your car tires were skidding and you're curving on a bad road? Now, what you are, given that it's skidding, you're not going to be applying your brakes. By and large, the primary parameter you have control over is the speed at which you're going. So, how fast you push the pedal. Now, most roads are curved in a way that there is a certain speed at which the wheels will not skid. So, if you're turning this way, then you're likely to be thrown outwards. So, roads curve a little bit, pointing you inwards, so that at a certain speed, you won't have any movement outwards or inwards. So, there is a certain correct speed. Now, if you're roughly within, if you're exactly at that speed, you'll stay spot on at the same point on the road. But you've got some margin for error. And if you're slightly higher than that speed, you'll slowly go to the outer edge of the road. But by the time the curve finishes, you might get there in time. Or if you're slightly under speed, then gravity might push you slowly towards the inner side of the road. But by the time the curve ends, you might still be within the road. So there is a small margin for error. So here, the error function is, if I'm within a certain range, then I'm okay. There's no loss whatsoever. Going to the left edge of the road or the right edge of the road is not going to harm me in any way. So there is 0. But beyond that point, the error there is 1. I could have an accident beyond that range. So within a certain range, I have 0 error. Beyond a certain range, I have different error. What if I were setting a Pipet's knob? So I'm doing this chemistry experiment, and I've got let's say, iodine trickling through the pipette, and I've got this knob that turns the speed of the flow of iodine up and down. Now, turns out that here, in most reactions, the error is cumulative. That is, if you set the knob fairly high, then slowly the concentration of iodine starts building up faster and faster and faster. So that after about, let's say, 1 second, you got, say, 1% extra. After about 2%, after about 2 seconds, you got the 1% extra from earlier, and you got new iodine, which is further compounding the reaction. So you got 1% for the first second, 2% for the second second, 3% for the third second, which keeps adding up, and it has a square effect, which means that if your speed is higher by 1%, and let's say that causes a 1% problem. If your speed is higher by 2%, that causes a 4% problem. So this is a case where the error function is a square error function. Let's say you are setting the price, the wholesale price per kg of rice. Now rice is a commodity. If you set it to be the lowest in the market, pretty much everyone will come to you. If you set it to be anything other than the lowest, you are not likely to have any benefit. And if you set it lower than the lowest, then, well, you'll still get some money. Your margins may be lower. So this is a case where beyond a certain point, my error function is 1. But below that point, it's a straight line. My profits just keep dropping. So let's say that the current market price is somebody selling it at 5 rupees, somebody selling it at 4 rupees, somebody selling it at 3 rupees. If I sell at 3 rupees, then everybody will come to me and I'll make a profit of 3 times X, where X is how many kgs of rice I have to sell. If I sell it at 2.5, my sale will only be 2.5x. If I sell it at 2, my sale will only be 2x. But if I try and sell it at 3.5, my sale will be 0, because they'll all go to the guy who's selling it at 3. So it increases up to a point and then 0. Various kinds of error functions. Most people don't get into what is the impact of getting something wrong, but that is quite crucial. Let's look at the pattern of some of the common error functions. We covered absolute loss. Now, absolute loss was the case of the index fund manager, where if he made a mistake this way or that way, it doesn't make a difference. He's supposed to get to this value, and his loss is as he goes away from this value, whether he goes this way or that way, his loss increases. There could be a 0-1 loss. You're writing an objective type exam. You either get it right or you get it wrong. So when you get it right, your loss is 0. When you get it wrong, your loss is 1. Finish. Or you're driving on the road. If your speed is between this range, you're fine. Beyond that, you could skid, and depending on the degree to which you skid, you could get a bigger or smaller accident, possibly. Or it could be a well-shaped function. That's another type of function. Or like for the pipette turning the knob, you ideally want this rate of the chemical mixing, but the further away it goes, the worse the effect. That's the squared loss function. Now,
Sorry, in previous slide, why is that not at 0? The first one?
let us say you want to target 0.1 return or whatever. The center could be anywhere. Now, depending on the, sorry, was that clear?
But if your bonus is based on your variation from the Sensex, then shouldn't it be?
That should be the Sensex.
Oh, that is okay.
That's okay. And this should be the target range of target speed that you want to get to. This could have been something else as well. The position doesn't matter as much as the shape of the curve just yet. So, given that actually I'm going to come back to this. What I'm going to do is take a simple data set and play around with it and see what happens when we apply various data sets to it. And more importantly, so there will always, for a given error function, there will always be some one number at which the error function is minimal. There often is one number at which the error function is minimal. For example, if it's a 0-1 loss, then there is one correct answer. Or if you're tracking an index fund, then you want your returns to be exactly at the value of the index fund. Given any data set and applying an error function to it, it's possible to figure out what that number is. Let's just try it in Excel and play around and see what the number turns out to be. Delete all of this. All right, I'll take the numbers. Sheet. Okay, so let's say the numbers are 1, 1, 2, 2, 2, 3, 4, 5, 6, 7, 10. I've sorted them for ease of use. Let's pick the first error function that we saw there, which is the absolute deviation from a number. Now, if these are the numbers that I get, and I pick some arbitrary number to represent what I ought to be looking at. So let's say I should be targeting 4. And let's calculate the error here. The error here is the absolute value of this number minus this number. So the error when let's say these are the values for every day. On the first day, I made a mistake by a magnitude of 3. Second day, again 3, 2, 2, 2, and so on. So what was the sum of my errors? 25. Now, is there a number that minimizes this error? Because if it does, then I could say that for this data set, that's sort of the middle number. That's the one that minimizes my error this way or that way. Let's try it out. At 1, my error is 32, 25, 24. It's coming down. Now it started going up again. And it keeps going up. That's one of the characteristics of most error functions. It tends to be, it's around the point where it's the minimum. It goes up on either side. So it looks like at 3, this is where it's the minimum. Now, so 2, it's 25, 3, it's 24, 4, it's 25. So 25, 24, 25. 3 is at the center. What about 3.1, 3.2? Let's try. 3, that's 24. 3.1, 24.1, 3.2, 24.4. Okay, let's go the other way. 2.9, 24.1, still higher than 24. 2.9, still higher than 24. So it looks like 3 is spot on, and 3 is where I have the exact middle value for this error function, which is mean absolute deviation. Or let's just call it average of absolute deviations. Let's take another error function. Pick one. You want to choose one? If you want some error function you are using here. Sorry.
0 1 loss.
Let's try 0 and 1. Okay, let's see what this looks like. Now, if I'm guessing the number 3, or if I believe that 3 is the central number, then my loss is if this value is exactly equal to this value, then my error is 0, otherwise my error is 1. Let's add it all up. That's the sum of all of these numbers. Now here my error is 10. Let's go through the numbers one by one. 0, my error is 11. So in 11 cases I got it wrong. I got it wrong in 9 cases if it's 1. That's sort of obvious, right? Because there are 2 1s. So if it's 1, then I got it right twice and wrong every other time. If I say 2, then I get it right thrice because there are 3 2s. If I say 3, I get it right once. There's only 1 3. 4, I get it right once, and so on. So 2 is where I get the least errors because there are maximum number of 2s. And that's another measure of what number is giving me the least error. Let's try something else. Let's try this epsilon sensitive thing, which means that it's okay to be within a certain range, and within that range things are fine, but beyond that range I start having problems. So that one way of representing that, just call it range error. This function doesn't really have a proper name. So let's take a value of 2 as a starting point. If this number, or the absolute value of this number minus this number is less than, let's say 1.5. I could go 1.5 this way or that way, things are fine. And if it's less than this, then I don't have any error, otherwise I have an error. Let's see what that does. So what it's saying is, if you pick 2, then in this range, you're fine. All the values are within 1.5 of this value. But beyond that, everything's high. Let's sum it up. So if I take 0, I get an error of 9, 1, I get an error of 6, 2, I get an error of 5, 3, I get an error of 6, 8. So it looks like 2 is where it's a minimum. Now let's try the few values a little bit this way, that way. 2.1, 2.2, doesn't seem to matter, 1.9, 1.8. So this is one of those cases where I could have any number, plus or minus. So it's not like 2 is the only number that minimizes the value. I have a reasonable range of numbers where, if I say that's the middle of all of these numbers, I still have the same error as the others. Sort of like driving a car, and when you're trying to skid, if you said what speed should you pick? Pick anything between say 70 to 75 kilometers per hour on this curve road, you're fine, doesn't matter. There's no such thing as 72 is a better speed than 73 or 71 is a better speed than 72. Everything in this range is fine. So it looks like everything in the range of 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.51. Okay, so anything above 1.51 and less than 2.49. So between 1.5 and 2.5, non-inclusive. That gives me the same error. The same 2 for. Let's look at squared error. So that's if I pick the value 2, then power of this number minus this number squared. So if I sum it all up, let's start with 0, 249, 174, 221, 390, it's coming down, 481, that's even lower, 594. Now it started rising, so 4 was probably the least, or at least the closest wrong number. Let's see if 3.9 does better. 3.9, 80.91, that's lower than 81. So 3.9 is actually slightly better. 3.8, no, that's gone up to 81.4, not quite good. So somewhere around 3.9 seems to be, at least for the first decimal place, the best central value. Now notice you got this number 3 minimizing the average of absolute deviation. This number 2 which minimizes the loss on a 0-1 scale. This number 2 again which minimizes the ranged error. 3.9 which minimizes the squared error. Now what does all this mean? It means that depending on what your loss function is, the value that you pick to target varies. Okay. Let's say, for example, that these were the stock prices over the last 11 days. Now, these were the Sensex values, Sensex returns over the last 11 days. Now, my wife comes to me and says, look, what I want you to tell me is, I know you're going to make a loss every day, that's fine. But I want you to tell me what loss are you most likely to make. Look, I want to have an estimate of what your bonus is going to be. Just tell me a reasonable figure. Now, because my loss is based on the average of the absolute deviations, I'm likely to say, look, by and large, I'll be off by 3 percentage points. So for every percentage point, if my bonus goes down by, let's say, a lakh a year, then my bonus will be 3 lakhs less than the best that it possibly could be. If I had perfect foresight and I knew exactly what the Sensex was going to be, my loss would be 0. But because I don't have perfect foresight, my loss will probably be around 3 lakhs. Whereas in the pipette case, if my chemistry teacher said, look, I know you're going to get this wrong, but do you have a sense of how far off you will be? Because I want to check if you're going to blow up the lab or things are under control. And then you'd say, okay, I'm probably going to be off by about 3.9. Now, let's look at some of these numbers a little closer. This 3.9 is actually the mean, the average as we know it, of these numbers. In fact, if I put a 3.909091, you'll get the lowest possible value that you get here. if I take the median of these numbers, that will always give me the lowest value for the average of the absolute deviations. If I take the mode, I don't know if this is a mode function here. If I take the mode, which is the most frequent of these values, that will always give me this particular one. I have no idea what analytical number gives you the range there. There are various kinds of error functions. For some error functions, there are simple calculations that get you the answer. So if you want to say what is the average of a bunch of numbers, then there are many ways to calculate an average. And the way you want to pick an average depends on what happens if you get the average wrong. So the first question to ask when somebody says, look, give me an average is, what do you want it for? What happens if I give you 75? Just I'm going to pick a number out of my hat and say 75. Now, we both of us know that that's wrong. So, but what is the impact of getting it wrong? If you're setting the price of a product, then what is the error function? If you're driving a car, then what's the error function? If you're participating in an election, what's the error function? And that will determine what number I take. Because if you said, for instance, give me the average of the voters, give me the average of the voting statistics, let's say. Okay, the error function is if I voted for the right person, then it's 1. If I voted for the wrong person, it's 0. So the error function that I want is the mode. That is, who's been voted for the most, which person has got the maximum number of votes. So I just say, this person has 1. That's the statistic you're interested in. If your error function, like for the tracking index, is symmetric across the center, I'd say, okay, you want the middlemost value, and that's the average that I'm going to give you. If for any reason your error function is a squared error, then I'd say I'll give you the arithmetic average, which is the sum of all the numbers divided by those numbers. To recap, so if you have an absolute loss function, the median is your average, if you will. If you have a 0, 1 loss function, your mode is the average. If you have this epsilon sensitive thing, then there's this complex formula for it. Let's not even bother going into it. There are some functions for which there are complex formulas. There are some functions for which there are simple formulas. In fact, there are only 3 that I know that have reasonably simple formulas. If it's mean, it's a squared loss. Now, let's take some of your projects and see what kind of loss function you have. Anyone wants to pick a project? Other than the Mahabharata? Or anything to do with that? Yes.
Yeah, so comparative ecology.
Okay. What are the numbers you're mentioning?
We haven't decided yet, but I mean, just for the sake of your question, maybe like, for example, species distribution across a particular geographical area.
Okay. So let's say we've got a number of taluks or cities or whatever, and we are counting the number of, and let's say there are 10 species, 10 taluks, and we want the number of birds in each of these. So supposing I said in all of these taluks, in all of these, for all of these birds, the number that you would have spotted in the last year was 10. Obviously I'm wrong. Now what is the impact of this error? If the actual number were 4 instead of 10 for a particular place, how bad would that be? Is 4 versus 10 as bad as 9 versus 10? Or is there a big difference across all of these? What do you think? So let's say the correct answer is 10. Okay. You give an answer of 4 and you give an answer of 9. How big is the difference? Which is one more correct than the other? First question. If one is more correct, then how much more correct is it?
The nine.
Sorry?
Intuitively, it feels as though one has more correct.
Fair enough. And it, by and large, because I mean it's entirely up to the people that are in the domain that know this. So you'd say, okay, 9 is more correct. Fine. So 9 has a difference only of 1 and 4 has a difference of 6. So is it 6 times more correct? Would that be a fair statement? Or is it, okay, I'll give you 2 choices. Is 4 36 times wronger than 9? Or is it 6 times wronger than 9?
36.
Say, getting a number of 4 is 36 times as bad as getting a number 9.
9.
Let me pick instead of 36 another number, 72. No, I mean, on what basis did you say that?
Just sounds right.
Sounds right? It might well. No, is that what everyone else would say? You have the same project?
Yeah, it's like, doesn't it depend on why they
Yeah.
want that?
Good question. What difference does it make? You know, sometimes after all this analysis, we do want to ask the question, why? What did I get this wrong? You know, so in the presentation next week, if you said, so we taken the average of all the marks or whatever, and we find that boys score more than girls. Everybody fails in mathematics. There isn't a single student who fails, who has passed in mathematics, and the state of education is one of the tops. What's the fact? So what?
We need to have some sort of background. For example, we can say that 1 equals 50% off,
Yeah, what-
but 1.2 would mean 90% off.
Good guy. Absolutely.
So we need to know that
You need
whether
to-
it's an arithmetic progression or a geometric.
But even arithmetic, I mean, apart from progression, if you are off by a certain amount, how bad is it?
Yes.
That's precisely the question. So I'm saying that when you're counting the species in a place, then if you're off by 1, how bad is it? If you're off by 2, how bad is it?
Yes.
That depends on the number of species itself. It depends on the population of the.
Doesn't matter. So let's say your species, you have 10 species or 10, 20 species. You're wrong by either 1 or you're wrong by 2. Now, how much worse is it to be wrong by 2 than it is to be wrong by 1, if at all? You could say being wrong by 1 is as bad as being wrong by 2. Or you could say it's worse by a factor of 2. You could say it's worse by a factor of 4. You could say worse by a factor of 10.
Then it becomes a systems issue here. Because there's this story you say that if you kill one tiger in Nagarhole, then it means so many liters of water less for Bangalore city.
Quite possible.
And if it is 2, then you can have.
Very
Compounding.
fair. So one might argue here that if we are off by a small number, that has a significantly smaller impact than if you're off by a larger number. So which might be a justification for the hypothesis, for instance. Now, you may be able to get a quantitative answer for it, you may not be able to get a quantitative answer. If you're not able to get a quantitative answer for it, then it's easy, it's sort of convenient to pick between some of these functions that you chose. Mainly because they tend to have reasonably simple averages. So in this case, we may say, okay, it's a squared error, so therefore we want to choose the mean. Let's take another example. Pick any other project. Is anyone working on any other project?
School marks.
School marks. Okay. So let's say a student, you said a student got a mark of 37 in mathematics, and somebody else said mark of 38. So if you could be off by 1 mark or you could be off by 2 marks. Is when you get it wrong by 2 marks, how much worse is it than if you're getting it by 1 mark? Is it the same? Is it equally bad? Is it?
It's more complicated because there is a pass mark 35, right? So beyond that,
Okay, so let's leave aside the pass mark for now. Let's say, so we're comparing a student who's got 90 and you say his mark is either 91 or 92.
I think it makes a difference as you go higher up.
The admissions are going to be determined. That's good thing that
Get the cutoff.
the point one also makes error is also not.
Which is an interesting thing. So if you're doing an analysis saying that this is the pass mark or this is the admission cutoff, then your error function is a step function. Which means that if it's less than a certain value or more than a certain value, then you've gotten it right, and beyond that you've gotten it wrong. In which case, the analysis becomes very simple. You're saying, here's a cutoff, how many people have gotten more than this, how many people have gotten less than this, and I don't care about the averages of all those, I just care about the counts. Okay. In which case, you would never ever take the average, median, mode, or any of those numbers. All of your analysis will only be based on cutoffs. Is there any reason why you might want to take the average of marks?
how would you compare performance across districts or boys versus girls?
Okay. So now the problem is I want to compare performance across districts. Okay. So what happens if I get the district performance off by 1 mark or 2 marks?
With this compared, so
Rank will change.
No, the rank will change. Again, my question is, if you get the marks wrong by 1 mark, So let's say Sirsi is the best district. Okay. You get that wrong by 1 mark versus you get that wrong by 2 marks. Would you say that the magnitude of the error is twice when you get it wrong by 2 marks, 4
Depending-
times when you get it wrong by 2 marks?
Depending the variation of
Yeah.
each district's performance.
Depends on
Suppose
how
it's
close the
really
district
close,
is.
then it will change your ranking. I mean your whoever.
But let's assume it's not really close. We have data that's large enough that the errors are likely to be substantially smaller than most cases. Let's assume it is really small.
If I only get CC wrong, then the magnitude will be more. If I get for all the districts wrong, it doesn't make it.
As long as you get it on the same way.
Yeah.
The
I
same
get wrong,
error,
I get
yeah.
plus.
Assuming they use the same function, error, I mean, they'll be similar.
Getting it wrong the same way is actually the same as getting it right. I mean, the reason why we get it wrong is because we get it wrong in different ways. You systematically, it's like, when I aim and shoot, I shoot exactly 3 inches to the right. I have to just correct it by 3 inches to the right or subtract the final answer.
You know the first line of Tolstoy's Anna Karenina. All happy families are alike. All unhappy families are different, are unhappy in their own way.
Errors are all unique. It depends on you, but you may want to say that being off by 1 mark versus 2 marks is roughly linear here. That is, being off by 2 marks is twice as bad as being off by 1 mark. In most cases, at least in business, if you get sales wrong by 1 lakh versus 2 lakhs, then the impact is usually linear because you pay tax on the sales, and tax is say 35% of your sales, and if you misreport it, either which way, you have a linear error. Or let's say you were looking at, let's take some other problem. Let's say you were counting the number of users in, for your, let's say, telecom operations across each of the districts, and you make decisions based on that. If you get the number of users wrong by, let's say, 50 users, then most likely your marketing budget will be, you will have a deficit in your marketing budget or a surplus in your marketing budget, both of which could be roughly equally bad. And that, being off by 50 users is about half as bad as being off by 100 users. In most business circumstances, that is the case. Which means that the median would be the more appropriate function to use in those cases. If it turns out that in your case, the error is exactly the square of how wrong you are, then the mean would be an appropriate function to use. Now, which begs the question, how often is it that the error is exactly the square? This is true in a reasonable number of, in science, this is often. So for instance, energy is proportional to the square of the distance. You take a spring, you compress it by x, the amount of energy that's stored in the spring is proportional to x squared. You've got acceleration, which is proportional to d squared. You've got a number of things that are proportional to the square. Most force fields are proportional to the inverse square of the distance. So at least this whole concept of squaring comes relatively naturally in the sciences, and in fact probably comes as naturally as linear relationships in the sciences. In business, it's very, very rare that you'll find anything that's based on the square of the data. Outside of that, in a lot of cases where we have data, we're just counting stuff, and neither of these, it's neither linear nor based on the square. It's usually you get it right or you get it wrong, in which case you're looking at the mode. So what I wanted to stress upon is the measure of centrality. When we say average, we typically think I am going to take the mean, which is sum all the numbers divided by the total number of numbers. That will give you the central number only if you have a squared error function. What you're implicitly saying is that, therefore, if I'm off by x, then my error is proportional to x squared. In most of your data sets, that's not the case. Just be very careful about using the mean as a centrality. If your error function is linear, you probably want to use a median. If your error function is a 0 or 1, that is, you either get it right or you get it wrong, you want to use a mode. Examples of this, elections, examples of this.